Thank you. Thanks for the invitation to be here today. I'll be discussing sparse-input reanalysis, in particular the 20th century reanalysis version 3, which I helped develop, and how it captures 200 years of weather using just surface observations. And of course, this is joint work. I listed a few of the main colleagues I have, but it's a huge, huge project. I wanted to start with an acknowledgement. We heard a little bit this morning about the impact that Eugenia Kalnay had on our field as well as the field of data assimilation. And I think her NCEP-NCAR reanalysis paper has 35,000 citations. And this data set is still used, for better or worse, but 30 years later. So I think that really speaks to her impact and the impact of that paper. So I'll start with just a bit of a motivation for sparse-input reanalysis in particular, and then I'll talk a bit about 20CR, the 20th century reanalysis version 3, its methods, its performance. I'll try to sort of briefly go through that because I've sort of presented this in previous conferences. And then I'll talk a bit about some recent applications, in particular to fire weather, as well as the future of 20CR and broadly what we're thinking might be possible. So why do we need reanalysis to span over a century? It really helps bridge the gap between weather and climate, right? These data sets are on sub-daily resolution, but they span climate timescales. They also allow us to put recent extreme events in a consistent long-term context, and it gives us a larger sample of these extreme weather and climate events so that we can do more robust statistics. I have a list here of things that these reanalyses have been used for in the past. There's very specific historical events and seasons that people have looked at. There's also more applicable reasons to today, risk assessment for insurance and reinsurance purposes and planning for renewable energy and coastal defense. What I have in bold on the bottom right here is validation and verification of paleo reconstructions and climate model projections, and I'll show that in the next slide. And then, of course, training ML models. To my knowledge, actually, I don't know of ML models that have been trained on any of the centennial reanalyses. I'd be really interested if any of you know of any of these uses, but it's definitely out there as a possibility. So reanalyses really provide an instrument-based link between paleo reconstructions and climate model projections. And this kind of exemplifies that. This figure shows global 2-meter temperature anomalies. Paleo reconstructions are the brown curves that sort of obviously extend way back in time. And then our climate model projections extend out into the future. And the reanalyses are all the other curves here in the middle. And the black curve is the 20th century reanalysis version 3, 20CR version 3. Linking these two matches kind of everything else on here pretty well, which is nice. And these are 2-meter temperature anomalies, but 20CR is completely independent of any land surface temperature observations. We're only using sea surface temperature observations and surface pressure observations. And so even with that, we still match this temperature metric pretty well. So Dr. Kobayashi nicely kind of introduced a lot of this morning, so I don't need to spend too much time on the difference between full input and sparse input reanalysis. Again, the motivation for having these two different types of reanalysis is issues with the observing system that can cause spurious trends and signals when we have huge changes to our observing system. Full input reanalyses don't go back far enough, right? We heard the balance between how long these reanalyses can be and how accurate they can be. But even if we only limit the time that we're going back and we're assimilating as much as we can, they can still be impacted by instruments coming online. And sparse input reanalyses only assimilate a few observations, so they're going to be less accurate, but they can extend further back in time. They have less impact from changes in the observing network, of course, because they're only assimilating one platform, but the density of that platform changes still in orders of magnitude, and so that is still a challenge. So again, the challenge with reanalysis in general, in particular centennial reanalysis, is that the observing network changes significantly in time. We saw this example earlier too, is that if you look at time series of precipitation, reanalyses in general don't match very well. This one in particular, you can see there's this sort of change in the signal, the variability, the trend coming from the ATOVs coming online. And I'm not trying to pick on MERA here. We've seen lots of other examples of all reanalyses really suffer from from some sort of issue, even ERA 5 with the background errors needing to be retuned for because of the ATOVs as well. 20CR, since it doesn't assimilate any radiances, we don't see this jump right at 1998 where AMSU comes online. But because we don't assimilate any radiances, we're not going to be as accurate. And so from this plot alone, you can't actually say which of these curves, which mean is better. You can sort of infer that the trend in MERA is probably not real here, but it doesn't mean that 20CR is right, of course. So turning to centennial reanalysis in particular, even if we only assimilate surface pressure, we still have huge changes in the observing network. So these are just heat maps of the surface pressure observing network from 1905 and from 2005. And you can see the huge 4 orders of magnitude change. And so even though we're not having to deal with satellites coming online and addressing model biases, we still have to think about this in our data assimilation methods for how we can handle something that's going to change over orders of magnitude in hundreds of years. So, all right, how do we do this for the 20th century reanalysis? Just to kind of give you an overview for those of you unfamiliar with it. It's a global 200-year history of subdaily weather. So this is an atmospheric reanalysis, and we only assimilate surface pressure observations into a modern weather model. Version 3 estimates temperature, wind, precip, all the atmospheric variables pretty much you could want and more, hopefully, and some land variables as well. We prescribe sea surface temperature. We refer to it as iteratively coupled, and I'll talk a bit later about what that actually means, but it's really a prescribed field. We also prescribe sea ice concentration and radiative forcing, 75-kilometer grid, 3-hourly resolution, and we go back to 1806, but only up until 2015. I'll talk about that too. We use an ensemble Kalman filter for our data assimilation method, and this helps us quantify our uncertainty. And then we have a website. All our data is publicly available. So one of the keys of being able to go this far back in time and using such sparse observations is to have flow-dependent covariances from that ensemble Kalman filter. And this was shown in Gil Campo's paper on the feasibility of such a reanalysis back in 2006. This figure is from his BAMS paper on the right here, is the RMSE of the Z500 field using surface pressure observations with 1905 densities. So that was about that left panel that I showed earlier with the heat map of observations. And what we see, the green is what's referred to as a climatological ENKF. Basically, there's no dynamic model, physical model, it's just climatological ensembles, climatological covariances that assimilate observations. The 3D VAR is in pink. There was, I think, some tuning for the 3D VAR to try to match the 1905 observing network, but even with that, it only does slightly better than just the climatological ENKF. Whereas the full ENKF, where you're evolving your ensemble forward with your model, and allowing those ensemble covariances to determine your data assimilation update really provides a significant improvement. So this is one of the keys to being able to do sparse input reanalysis is the ensemble Kalman filter. So I've talked about this in previous presentations as well, but there was the previous version of 20CR, version 2C. Relative to that version, we have several system improvements, a newer, higher resolution forecast model, more observations because data rescue is an ongoing activity. So every time we do a new reanalysis, we have more observations. We improved our observation quality control methods, and we improved our DA methods. And this last point kind of comes back to what I had mentioned for the challenge of historical reanalysis that has this 4 orders of magnitude change in the density of observations, is we need to have methods that actually address that. And so well, the 4D IAU, I sort of show an issue on the left that's not as much relevant for the observing network changes, but for adaptive localization and adaptive inflation, these two figures in the middle on the right kind of show how these methods are adaptive to the density of the observing network. So they really let our methods work for 200 years without really having to do any tuning ourselves. These methods just adapt to the changing observing network. All right, so moving on to performance. We have here just the fit to surface pressure observations, our RMS O-Fs. Previous 20CR version 2C is on the top, and the newer version 3 is on the bottom. The blue curve is just the number of observations assimilated each cycle. So you can see, especially in the bottom panel, that 4 orders of magnitude change from 1806 to 2015. The solid line is our actual RMS error between our obs and our first guess. And the dashed line is our expected error. And this is a function of the observation error and the ensemble spread. And so our actual and expected errors should be close to each other. And for version 2C, it looks pretty good. You see the errors go down as the number of observations goes up. And the actual and the expected errors are pretty close, although you see some discrepancies, particularly in the 19th century here. So version 3 is improved. We go further back in time. We match the actual and the expected errors pretty well all the way back to 1806, which is, I think, I worked on it and I still think it's impressive. And then the only thing is our expected errors are a bit too high in the modern period, or in other words, our ensemble spread may be too large. But in general, our errors are consistent with the expected errors for the entire 200 years, despite those changes in the observing network. And this result is not tuned. Again, we're just using these adaptive methods for data assimilation, and this is just kind of what we get, which is great. So we can also compare to more modern reanalyses, ERA 5. These are just Z500 errors. Blue is version 2C and red is version 3. The thick lines are the error and the thin lines are the ensemble spread. And so you see that version 3 basically has lower errors and they're more consistent with the ensemble spread. The gray shading here is the operational forecast skill in the Northern Hemisphere. And so you can see that our errors for version 3 are comparable to modern, this is actually maybe 5 or 6 years old now, operational forecast skill in the Northern Hemisphere. All right, so that's all sort of older work, I guess. I want to talk about an application. This next few slides are from Gil Campo. So I'm not directly involved in this work, but I think it's pretty cool. So fire weather monitoring. So in 2021, Congress authorized NOAA to improve wildfire research, prediction, detection, forecasting, monitoring, data management, and communication and engagement. And they basically produced this Disaster Relief Supplement Appropriations Act. Appropriations means money, and so money from Congress came to NOAA, and specifically via this grant to Gil and Prashant Sardeshmukh to use the 20th Century Reanalysis version 3 for wildfire monitoring indices. There's 3 basic ingredients for fire weather. It needs to be hot, it needs to be dry, and it needs to be windy. If you have these 3 things, it's a red flag day, right? So we're going to use 3 quantities from 20CRV3, 2-meter temperature, 10-meter vapor pressure deficit. I'll be honest, I don't totally understand that, but it's a measure of moisture, and 10-meter wind speed. And so what we have here is the rank correlation in shading between 20CRV3 and ERA 5 data for 2-meter temperature, 10-meter winds, and 10-meter vapor pressure deficit. And then in the contours is the confidence from 20CRV3 from our ensemble. I've defined confidence on the right. Basically, it's how spread out our ensemble is or not. So the blue colors are high correlation between us and ERA 5. The white and green colors are less correlation. And then the red contours are high confidence, orange is medium, and the white contours are lower confidence. And basically what I want you to pull away from this slide is how well it matches where we're highly confident. We also are correlated highly with ERA 5. And where we're not confident, so look at vapor pressure, for example, where we're not as confident, we don't correlate as well with ERA 5. And we can look at this as a sort of a scatter plot as well if we're just looking at individual points and looking at the confidence that's on the x-axis compared to that rank correlation on the y-axis. We see the same thing, right? The lower confidence has lower correlation, the higher confidence has higher correlation. This suggests that 20CRV3 confidences are reliable, and they can be used to estimate the quality of our indices. So of course we can make these fire weather indices with 20CR, but the question is, can we trust them? And the answer is look at the ensemble spread, and that'll tell you if you can trust them. All right, so moving on now, sort of moving towards the future. One challenge with 20CR v3 is ENSO representation. So we really don't have much of an ENSO before 1871. This is 2 meter temperature over about the Niño 3.4 region. 20CR is in red, Serra 20C is in blue, just for a comparison. And you see 1871 right around here. There's variability after it, and there's not much variability before that. So I said earlier that 20CR is iteratively coupled, and I said I would tell you what that means. So the first version of 20CR, called this 20CR v2b, used HADI SST1 for its SSTs from 1871 onwards. And before 1871, we used climatology, so right here. That atmospheric reanalysis was used to force an ocean reanalysis, so DASI-2, for 1846 to 2012. And then that SODASI reanalysis was given back to us. 20CR v2d used SODASI from 1846 to 2012, climatology before that, and then that given back to SODASI. They made another reanalysis, came back to us for 20CR v3. So even though, when you look at the details of 20CR v3, we have SODASI, which is used from 1815 to 1980, and climatology before that, because of this 1871 in the very first version of 20CR, we have issues with ENSO prior to 1871. So even though it's pretty cool that our SSTs have seen earlier versions of 20CR, and so you can kind of get this very sort of broad coupling, we still have this issue, particularly with ENSO. So this is just another visualization of what I mean here. So 1871 in this red line, we have variability after in the, sorry, this is the time series, and this is latitude on the x-axis. You see the tropical variability after 1871, and not much variability before 1871. So a few, well, what we're looking at for the future of 20CR. First, we are planning to extend 20CR v3 beyond 2015. It's quite outdated at this point. One challenge I'll mention is that the SST dataset we use for the modern period, HADI SST2, ends in 2015. And so we need SSTs. We don't have a coupled model for 20CR v3, and we need to figure out how to produce what SSTs to use and how to then produce an ensemble, because our ensemble is a key feature of our reanalysis. We can't just duplicate one SST 80 times, so we're going to lose a lot of our spread. And thanks to colleagues at Reading, it seems like this will happen. We'll likely extend 20CR to at least 2020, hopefully 2022, in some future time period. So, but looking forward to 20CR v4, again, data rescue, super important. So we'll have more observations for sure. Apparently a lot in Europe, which will give us smaller errors, greater confidence, and we might be able to go further back in time. And then there's a few other points that I'll go through that are all sort of questions, and I'll go through these one by one. So additional observation types. We have looked at assimilating wind direction. This is some work that Gil and Chesley McCall have been working on, and then there is a paper by our colleague at CU Boulder looking at assimilating wind direction. We would try not to assimilate wind speed because it has issues with trends, because ship masts get higher and then the measured wind speed gets stronger, and then you see this spurious trend that's not real. We also, I think it's really important to look towards having a coupled ocean atmosphere system. Potentially, we could use the future operational NOAA unified forecast system that we heard about earlier this morning at a course resolution. Or our colleague Niraj Agarwal at NOAA is looking at producing a machine learning emulator for the ocean atmosphere, lands and ice, based on the UFS replay data set, which we'll hear more about later this week too. Other data-driven model possibilities, linear inverse model for the ocean potentially. This is work that Gil has been thinking about, or using some of the existing machine learning emulators for the atmosphere, figuring out what to do in the ocean. And this is work that I'm doing with Jeff Whitaker. And so just to kind of take a small detour for that, The question is, can we use these emulators to assimilate surface pressure with an ENKF? So could we do 20 CR V4 with GraphCast, for example? And the answer right now is no. So this is the sea level pressure increment from GraphCast after just a week of cycling. And you can see this super high frequency grid scale noise. Eventually GraphCast, not even after more than a couple weeks, GraphCast goes so unstable that it diverges. And this is likely due to inaccurate representation of covariances, which is kind of an inherent issue with this model and would take a lot more work to try to figure out how to modify it to be able to use it for something like this. There are also stochastic, well, there's hybrid machine learning models where the dicore is based on physics, but then the physics themselves are learned. So we have a spectral dicore learned physics. Here is just Z500 error relative to error 5. The blue curve is basically using UFS, so this is kind of what 20CR is now. Orange is this hybrid model, neural GCM. And you can see it's stable, but its errors are pretty bad. And then the red curve is a deterministic version that's not stable. Basically, we need to consider data assimilation when training these models. So at the moment, these models can't be used out of the box for something like this. And then the last point I'll mention, we could use machine learning to learn the bias correction or learn model biases from a full input reanalysis. This is based on some work that Patrick Lelio at ECMWF has done, Seichun Chen previously at NOAA has done, and potentially this could allow us to assimilate all available observations as they come online and remove the need for sparse and full input. If we could learn all of the model biases, we would move, we wouldn't have that signal that we saw with MERA, right? We would know the model bias all the way back as far as we want, and we would not have to deal with that. But I think we're pretty far away from that at the moment. I just wanted to throw that out there as a possibility. Yeah, so that's basically it. I did want to sort of emphasize for that the machine learning models, even though we can't use them, I really like the sparse input reanalysis context as like a test bed for things like this. So it's just, if we ever wanted to use these machine learning models for even but modern operational numerical weather prediction, using something like sparse input reanalysis as a test bed really helps us answer that question and find those problems with those models. So, all right, thank you.